Okay, so in this video, what I'd like to do is explore the idea of a differential equation being equal to some kind of input, and then seeing what the response is based on that input. Now, we've always done that before, and in differential equations, that just means a non-homogenous differential equation. When you'll have something like the left-hand side being equal to a function of sort. So, for instance, it might be equal to e to the minus t, or at, or some kind of a function, or even a constant. And that always represents the input, whatever's on the right-hand side. So in circuit analysis, you might have the current being modeled as a differential equation or a second-order differential equation in a LCR circuit, and the input might be the voltage. The problem is that what happens if the voltage is not switched on before a certain value? So let's say you might have the charging or the discharging of a capacitor, and the charging only occurs after a certain period of time, maybe after t equals 1 or t equals 2. So for that, we're going to use the Heaviside step function to describe the oscillatory motion that takes place, but only with regard to a response that occurs at a point in time after t equals 0. So for that, we can use the unit step. And obviously, if there's a function that begins after a certain time, it would just be the unit step function, or the Heaviside step function with the product of that function. So if the input was something like e to the minus t, we would just use and say, it started after t equals 1, that would just be ut minus 1 e to the minus t minus 1. So let's have a look at a differential equation, and we're going to use the principles of the inverse Laplace transforms with regard to Heaviside step products to be able to solve this problem. So we've got here f dot t plus 3f of t equals ut minus 1. So the first thing that I'm going to do is just convert this to notation that we're familiar with. X dot plus 3x equals u t minus 1. And we said before that the Laplace transform of x can be denoted as x bar, which is f of s. And the Laplace transform of x dot is going to be s x bar minus x naught. And we don't need this for this, but I'll do it anyway. We said that the Laplace transform of x double dot is going to be s squared x bar minus s x naught minus x1, etc., as we've shown before. And we've also bear in mind that the Laplace transform of u t minus 1 is going to be e to the minus 1s on s. Yeah, because the Laplace transform of u t minus c is e to the minus cs on s. Yeah, and just we can also say that the Laplace transform of u of t equals 1 on s, and we can also say that the Laplace transform of u t minus c, f of t minus c, equals e to the minus cs f of s, providing that the Laplace transform of f of t is f of s. But it's clear that we're not going to need these transforms for this. We're just going to need the first one. So if we take, again, the Laplace transform of the left-hand side, we can say that that's going to be equal to the Laplace transform of the right-hand side. And using the principle of linearity, exploiting the principle of linearity, we can say that the Laplace transform of the entire left-hand side is going to be exactly the same as the Laplace transform of each individual component on the left-hand side. So we can say, if I write that out formally here, the Laplace transform of x dot plus 3x equals the Laplace transform of u t minus 1. And then we can say that the Laplace transform of x dot plus 3 times the Laplace transform of x equals the Laplace transform of u t minus 1. And remember how we used this method for solving differential equations before. We find the Laplace transform of the left and right-hand side, and then we find the inverse of that to get back to our original function. So we know that the Laplace transform of the first derivative of x is going to be x bar. So we can write x bar plus 3, oops, sorry, what am I doing? I'm going mad. X dot is s x bar minus x naught plus 3x bar equals the Laplace transform of ut minus 1, which is going to be e to the minus 1s on s. Okay, and we're also told that the initial condition is going to be x naught equals 0. So when t equals 0, f of t is going to be 0. So we can actually say that just the x bar plus 3x bar equals e to the minus s on s. And then we can take the x bar out, obviously, and just say x plus 3 equals e to the minus s on s. And then we can divide both sides by s plus 3. And that's going to imply that x bar equals e to the minus s on s plus 3. Now, do you remember before, what we normally would do is find this expression, x bar, which is f of s, in terms of its partial fractions. And then once we've done that, we can easily find, hopefully, if it's recognizable, the inverse Laplace transforms of all the individual components. And then, since the property of linearity says that the inverse Laplace transform of all the individual components is identical to the Laplace transform of the entire function, we can then find and state that the inverse Laplace transform of that must be the inverse Laplace transform of x bar. The inverse Laplace transform of x bar is the inverse Laplace transform of f of s, which is f of t. And that's how we can find f of t. So we've got here this thing. So how are we going to find this in partial fraction? So what we can do, we can just take the e to the s out, e to the minus s out, make things a bit easier for ourselves, and say that's going to be 1 on s plus 3 s. Yeah, 1 on s plus 3. And then if we find a partial fraction of that, and then just take the e to the s back in. So let's just go ahead and do that, which should be quite straightforward. So we can say that 1 on s plus 3 equals a on s plus b on s plus 3, which implies that s plus 3 plus bs equals 1. So when s plus 3 equals 0, s equals minus 3, so we can say that b equals minus 1/3, and we can say that when s equals 0, a equals 1/3. So we can now say, therefore, that x bar equals e to the minus s one-third dot 1 on s minus 1/3 dot 1 on s plus 3. So let's take the 1/3 out. So we can say that x bar equals 1/3 e to the minus s, 1 on s minus 1 on s plus 3. And now, hopefully you can see that if we take the 1/3 e to the minus s back in, we've got something to do with the second shift theorem going on, because we've got e to the minus cs and a function, which takes us back to this over here. We've got e to the minus cs f of s. So if we have e to the minus cs f of s, and we take the inverse Laplace transform of e to the minus cs f of s, that's going to give us the inverse Laplace transform of the Laplace transform of ut minus c f of t minus c, which is just the function, because an inverse Laplace of a forward Laplace cancels Laplacian operations, if that's an expression. So let's go ahead and do that. So we can now say that x bar equals 1/3 e to the minus s dot 1 on s minus 1/3 e to the minus s dot 1 on s plus 3. And I'm just going to rewrite that to make it a little bit easier for me in terms of the e to the minus s f of s. So we've got e to the minus s, and f of s here is going to be 1/3 dot 1 on s, and then we're going to subtract e to the minus s dot 1/3 dot 1 on s plus 3. So over here we can see that the f of s component is going to be 1/3 dot 1 on s plus 3, and the f of s component over here is going to be 1/3 dot 1 on s plus 3. Wait a minute, is that right? Yeah. And that implies then that the f of t is going to be 1/3 e to the minus 3t in both cases. So we can now say that x equals the inverse Laplace transform of e to the minus s 1/3 1 on s minus the inverse Laplace transform of e to the minus s 1/3 dot 1 on s plus 3. So e to the minus s, so the shift is going to be 1, so that's going to be ut minus 1, and the function is going to be was it right what I said here? No, it was complete nonsense, as usual. The function over here, this is not nonsense, this is good. But over here, the f of t is going to be 1, isn't it? It's going to be just 1/3. Because if f of s is 1 on s, f of t must be 1 times that by a third. So that's going to be dot 1/3, I think. And then we're going to subtract t minus 1, f of t here, which will be e to the minus 3t, 1/3 e to the minus 3, and there's going to be a shift of t minus 1. So, oh, that was brilliant because you couldn't see any of that. Sorry, I do apologize. So all I've done here is taken the inverse Laplace transform of that, and that's x bar. Okay, e to the minus s, 1/3 1 on s. So again, f of s is going to be 1/3 1 on s, so therefore f of t must be 1, and it's linear amplified, so by 1/3 factor. And the shift is going to be 1, so it's going to be ut minus 1 times 1, because the function is 1, times 1/3, minus f of s, minus the inverse transform of e to the minus s 1/3 dot 1 on s plus 3. So we can say that f of s is going to be 1/3 dot 1 on s plus 3. The inverse transform, so f of t is going to be e to the minus 3t dot 1 on 3. And the shift is going to be 1. So that's going to be minus ut minus 1 dot 1/3 e to the minus 3t. And because there's a shift of minus 1, it's going to be t minus 1. So now what we can say is that rather x, this is actually going to be f of t, because we let x equals f of t over here. So we can say that f of t equals, and we've got 2 ut minus 1, so we can take that out, ut minus 1. And we can take out the 1/3 as well. That's going to be 1 minus e to the minus 3t minus 1. So that's looking nice. That's looking like a nice kind of response. So let's draw that. Okay, so now that we've got a scale here, we can map this function as 1 minus e to the minus 3t minus 1. So this part is saying that the function is only going to turn on when t equals 1, which is going to be, let's say 1 is over here. It's going to be 0 for everything up until 1. And then we're going to multiply whatever it is by 1/3, the function by 1/3. So the function is 1 minus e to the minus 3t minus 1. So we can see that when t equals 1, it's going to be e to the 0, which is 1. 1 minus 1 is 0. So that's good. And it's going to kind of go like this, isn't it? And as t tends to infinity, this is going to tend to 0, and it's going to tend to 1. So the actual function should look something like that. Yeah? But we've got a 1/3 factor going on. So what it's really going to look like is that it's going to look something like this. And that's going to be 1/3 over here. And that's representative of this entire function. 1/3 ut minus 1, 1 minus e to the minus 3t minus 1. And that corresponds to the second shift theorem of what we saw before about mapping a function when you have the argument of the Heaviside step function, which is t minus 1. And that is exactly the same as the argument of the function that we're dealing with, which is the whole thing over here, t minus 1. When the arguments are the same of the Heaviside step and the function that is a product of the Heaviside step, it's exactly the same as the function, which is 1 minus e to the minus 3t, just shifted c units, so it's shifted 1 unit along. So, and obviously that's times by 1/3. So really, it would normally look something like this, and then kind of 0 up until this point, and then it goes like that. But remember, for t equals 0, all we've done is shifted this by 1 unit, so that the actual function now is looking like that. The other thing to note here as well is looking at the response, which is the blue line, and also taking into account the input. So do you remember we said that the input, if we go back right at the beginning of the differential equation, was what was it now? Here we are, ut minus 1. So if we look at ut minus 1 and what that would look like on the graph, ut minus 1 would look like, well, it would be 0 for all values up until 1, and then it would turn on and then go like that forever. That would be the input. So what's nice is that we can see very clearly that the response to the input step function of ut minus 1 is this blue line going on here. So this could be a voltage being turned on after 1 second, and the blue line might represent the say the voltage in the inductor, or the current in the capacitor, kind of leveling off like this when the voltage is turned on. So this is a very nice representation of what's actually happening, say with many applications, but one that comes to mind would be in circuit analysis. And this is a very easy way to solve non-homogeneous differential equations with unit step inputs. Okay, so let's have a look at another example. So here we have 5 f prime t minus f of t equals ut minus 4. So we've got a differential equation going on here with a unit step response when t equals 4. So something is turning on when t equals 4, and we want to know what the response of the function is going to look like. So first things first, let's convert this to Laplace notation that we're familiar with. 5x bar minus x equals ut minus 4. And I'll just put a little note here, f of t equals x. Let f of t equal x. And then we can say that the Laplace transform of x is x bar equals f of s. We can say that the Laplace transform of x dot equals s x bar minus x naught. We can say that the Laplace transform of ut minus c equals e to the minus cs on s. We can say that the Laplace transform of u of t equals 1 on s. We can say that the Laplace transform of ut minus c f of t minus c equals e to the minus cs dot f of s, providing the Laplace transform of f of t is f of s. So let's go ahead and take the Laplace transform of the left-hand side and the right-hand side. Exploiting the principle of linearity immediately, we can say that the Laplace transform of everything on the left-hand side is going to be the Laplace transform of all the individual components. So we can immediately say that that's going to be equal to 5 times the Laplace transform of x dot minus the Laplace transform of x equals the Laplace transform of ut minus 4. So we can now say that that's going to be equal to 5 s x bar minus x naught minus x bar equals e to the minus 4s on s. And a condition that we know that I should have put at the beginning, that x naught is going to be 0. That means that when t equals 0, f of t is 0. Yeah. So we can say that 5 s x bar minus x bar equals e to the minus 4s on s. So we can take the x bar out, and we can say that 5s minus 1 equals e to the minus 4s on s, and divide both sides by 5s minus 1. So we can say that x bar equals e to the minus 4s on s, 5s minus 1. So now let's take out the e to the minus 4s. 1 on s, 5s minus 1. And now we can say in the partial fraction notation, we can say that 1 on s, 5s minus 1 is going to be identical to a on s plus b on 5s minus 1. And that implies that a 5s minus 1 plus bs equals 1, identical to 1 for all values. So when s equals 0, minus a equals 1, therefore a equals minus 1. And when 5s minus 1 is 0, 5s equals 1, it's going to be a fifth, so s equals a fifth. So that's going to be 1/5 b equals 1, so b equals 5. So we can say, therefore, that 1 on s, 5s minus 1, is identical to minus 1 on s plus 5 on 5s minus 1. And then we can substitute that back into x bar. So we can say that x bar equals e to the minus 4s minus e to the minus 4s on s plus 5e to the minus 4s on 5s minus 1. Now, what we can do over here is we can take out the fifth, the 5. So I'm just going to do a little quick calculation over here, saying if we take out the 5 on 5, we're going to be left with e to the minus 4s on s minus 1/5. Yep. 5 on 5 is 1. So we can now say that x bar equals minus e to the minus 4s on s plus e to the minus 4s on s minus a fifth. And then we can now take the inverse transform and say that x equals the inverse transform of this plus the inverse transform of this, which is going to be minus. Now again, using the second shift theorem, which we have over here, we can say that e to the minus cs, e to the minus 4, so we can see minus 4s, so we can say that ut minus 4, the shift is going to be 4. And the function is going to be 1 on s, which is going to be equal to 1. So that's just going to be ut minus 4 plus the inverse transform of e to the minus 4s dot 1 on s minus a fifth. So we can see here that the shift, the c, is going to be equal to 4. F of s equals 1 on s minus a fifth. So that implies that f of t is going to be e to the 1/5 of t. But remember, there's going to be a shift going on. Sorry, couldn't see that. So all I've done here is just taken this down and said that we're going to have to look at the inverse Laplace transform of this function. We know the shift is 4. F of s is 1 on s minus a fifth. So the shift is going to be 4, c equals 4. F of s is 1 on s minus a fifth. Therefore, f of t, in this case, is going to be e to the 1/5 t. So now I can say that x is going to be minus u t minus 4 plus u t minus 4 dot e to the 1/5 of t minus 4, because there's the shift there. And now what we can do is say, therefore, that f of t equals u of t minus 4. And that's going to be minus 1 plus e to the 1/5 t minus 4. And if we were to kind of plot that out, we'll have f of t over here, t over here. We're told that the function only turns on when t equals 4. And the shape of this is going to look something like that. As t gets larger and larger, yeah. And remember, this is going to be 0 all the way up until that point over there. And if that's 1, we can say that the input is going to look like this. and that's ut minus 4. So we can see then very clearly that when we turn on something, the response is going to be this blue line like that.